Welcome to the 7th module of the training. In this module, we'll learn how a potential aggressor can bypass the firewall. Let's discuss the general method of bypassing firewalls. In one of the previous modules, we bypassed the Windows firewall using the DLL injection technique. We could do that, but there's a much better way by means of using the code injection technique, which injects the code directly. Let's consider which applications are present on the firewall whitelist. Surely a web browser, instant messenger, or mail client. They would be useless without internet communication. On the other hand, which of these applications are sure to be present in the computer? Obviously, the answer is the internet browser, so we'll use it in this module to fool the firewall. We have to pay attention to the fact that connections take place on specific ports. Firewall rules may state that, say, the application X may connect with the internet, but only on the Y port. Here we have some port numbers for various services, for instance 20 and 21 for FTP service, port 22 for SSH, 25 for SMTP, 80 for HTTP, 443 for HTTPS, or ports from 6661 to 6667 for the IRC service. That's why in our example, we'll use port number 80. If the browser has permission for outgoing connections, it will certainly be port 80 or 443. Mind you, we can't connect with the SSH server via, for instance, a mail client. If the mail client always connects via port 25 and suddenly it starts to use port 22, such behavior is definitely suspicious. In this case, it's better to ask the user to allow for outgoing connections, which any smart firewall will definitely do. But why should we choose the code injection technique if we can modify the browser file so that it sends a file unnoticed, or so that it's a go-between for other applications? Unfortunately, it seems that a smart firewall can detect a file modification based on its checksum and alarm the user. For each file, we can calculate the checksum using the CRC, MD5, or SHA algorithm. A checksum is characterized by which the change of even a single byte in the file causes the complete change of the checksum. However, what do we do if a web browser is closed? Users don't have to use it constantly. The attacker can't count on the browser to be constantly active. However, there is a possibility of starting the browser without opening the window in order not to raise suspicions of the user. If we entered the mind of a potential aggressor, we would first have to find the default browser, start it, and in the program entry point, overwrite the code with 2 bytes, usually called JMP EIP. This instruction is responsible for jumping to the same place, so it would cause the program to enter an endless loop. Then we could safely inject the code and close the browser. Let's try to execute such a scenario in practice. We have a server which includes 2 files, index.php and recv.php. The task of the recv.php file is to receive files, while the task of the index.php file is to show the files present in the folder. The code of both scripts is very simple. The program gets the file name, moves the file to the right place, and then decodes it using base 64. The index.php file opens its own directory and prints the lists of files, creating simple links to them. Now, let's start our enhanced keylogger, known from one of the previous modules, and check whether the firewall is informed about the fact that the logs are sent to the server. We've started our program and we can see that it's copied to its own starting directory. We write something on the keyboard and we see that it appears in the log. We have to wait a while for the program to send the logs and create a screenshot. The file with the screenshot should appear in the window. It will be sent and we'll be able to see the results in the browser. As we can see, the logs have already been sent. Now we can close the program so that it doesn't work in the background. We press F5. We see that 2 new files appeared. One with the log, which we saw earlier in the drive, and the other a screenshot. But most importantly, both files were sent, even though the firewall is enabled. If we tried to use the original keylogger from the fourth module, the firewall would instantly alarm us that something is being sent. Let's check how we modified the code of our previously used program. Here we have the version of the keylogger from the sixth module, where we did our best to lower its detectability. In the log CPP file, we included a function that sends the file. One of the functions is upload file, while the other is make zombie process. Let's start from the make zombie process function because it's precisely the one we need to start the process of sending. The make zombie process method creates a new browser process. We get the path to the application which handles the HTTP protocol and the action of opening the default browser. The path is present in the variable def_brow. We create a sleeping process so that initially its execution is suspended. We have to know that after the process starts, before anything is executed, we have the entry point address in the EAX register. So we can get the context of the thread, the handle of which we have in the process information structure, filled in by the create process function. We grant writing permissions in the place specified by EAX. We have to do this to write the 2 bytes there. To this address, we write the values EBFE, or the so-called JMP EIP. The moment we overwrite them, we can resume the thread using the resume thread function and return the handle to the process so that we can close it later. We also have the FWB upload function, where FWB stands for Firewall Bypass Upload, which takes parameters such as the file name, the host name, which is the address of the server for communication, the script, or the name of the script which takes the file, as well as the name of the file on the server. First of all, we create a process. We assign a handle to the hproc variable. Next, we upload and analyze this function. Further, we can see the call of the terminate process function, because after sending the file, we no longer need the browser process. Let's look into the upload file function. First, we get the file contents. Then we have to create the headers, which we'll use for sending it. We encode the buffer using base64. Mind you, we have to change the type of data to multi-part form data, which means sending data using a form. We can also see the number, using which we recognize the beginning and ending of the sent file. Content disposition form data, by which we inform the server that data is coming from the form. Next, we have to create the file header. We set the relevant content type as well as set the encoding to base64. Between these 2 character chains, we put the file contents encoded using base64. The header is ready. We'll send the files similarly as in the case of a remote console, but we've written all the operation in this shellcode. They're simply subsequent calls of the functions Internet Open A, Internet Connect A, HTTP Open Request A, and HTTP Send Request A. We call these functions one after another, but instead of calling them locally in our program, we inject the right code to the browser and call it in its process. After creating the headers, we have to inject the Wininet DLL library to the browser, because this library doesn't have to be loaded. Then we allocate memory for the Wininet DLL string, after which we create a remote thread, which we'll call the load library function in the browser. We wait for the loading to finish and get the exit code, which we'll need to calculate the function addresses, because addresses in our program and the browser don't have to be similar, due to possible ASLR. 。 We just need a couple of character strings, such as for instance the agent, which is what we pass to the Internet OpenA function. Or the host, that's the server address. We allocate memory for each such string and write it right away. We also need the post string because, as we remember, it has to be passed to the HTTP open request function. Obviously, we'll also need the name of the script we'll use. It's worth noticing that we get the function address in a rather specific way. We use the getProcAddress function to read the VA address. We subtract it from the image base of the WinInet DLL library in our program, and thanks to that, we get the RVA address of the given function. Next, we add it to the IB variable, that is, the image base of the WinInet DLL library in the browser, thanks to which we get the VA address, not in our process, but in the browser process. We get the header lengths and allocate the place for them. Then we write our headers to the returned addresses. We also see our shellcode. It's actually very simple, includes many instructions, push, 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 call, which require no additional explanation. Then we patch the shellcode with additional addresses. We won't discuss the entire shellcode here. We patch the usual way. We increase the beginning address by a place where the given value is supposed to be present. Further, we see the values which correspond to the addresses of variables which we've allocated and written. Now we have to allocate memory for our shellcode using virtual allocx, obligatorily with execution rights. We save, create a new thread, and wait until the sending is finished. Then we get the exit code. Even though it's not needed at this exact moment, it can be useful in later stages. Finally, we have to release all the allocated data. Let's check how the call on the sendLog function changed. We used to have the functions Internet Open, Internet Connect, and FTP put file here. We replaced them with the call of the FWB upload function. That is, the name of the file on our drive, followed by the address of the server which we worked on. Then the script name, which handles these calls, and the name of the file on the server. We have to use only the name of the file without the earlier path. We do the same with the screenshot. That is, we have the path to the file, the IP address, the script, and the name on the server. Let's summarize what we've learned in this module. We've seen how an aggressor can bypass an active firewall. The program worked in the background. The firewall was on, but it didn't notify us about the fact that a file was sent to the server. In this case, it was a log file, but just as well it could have been our password files stored in the browsers, private photos from holidays, or company documents. Of course, the firewall is a useful tool and it's good to have it installed. But, as we've just seen, sometimes it only gives us an illusion of safety. We shouldn't trust it entirely. We've also learned how to find the default browser and how to start it so that it's invisible to the user. Thanks for your attention, and please go to the next module. See you there.